Welcome back to Programming Fluency. This is section 12.3, Testing and Integration, the final section of the course. Your program compiles. It runs on your test file. So you are done, right? Not yet. You have tested only one input. In this video, you will test the program across every category of input, run val grind on every path, and turn a program that works into a program that is correct. Let's finish this. Your program compiles. It runs on your test file. It produces the right output. So you are done, right? Not yet. You tested one input. Let's turn a program that works into a program that is correct. This is the plan for this video. First, 4 categories of tests: normal, edge, error, and memory. Next, test input files. One file for every scenario you need to cover. Then an automated test script. It runs every test and reports pass or fail. After that, val grind on every path to catch leaks that show no visible symptom. Finally, integration and regression. The modules working together and no backsliding. Let's begin with a hard truth. You tested one input, a 2-line file with a handful of words. That is not enough. Does the program handle an empty file without crashing? A file where every word is the same? A word longer than 63 characters? A file name that does not exist, running with no arguments at all? Every one of these is a case a real user might hit. The difference between it works on my file and it is correct is testing, probing every category of input and verifying each one. A systematic approach organizes tests into 4 categories, and each one builds a different kind of confidence. First, normal tests. They verify correct output for typical input, the happy path. They tell you it works. Second, edge tests. They probe boundaries like empty input, a single element, or a maximum size. They find off-by-one errors. They tell you it is robust. Third, error tests. They verify graceful failure with bad arguments and missing files. They tell you it is safe. And fourth, memory tests. They catch invisible bugs like leaks and use after free. Only val grind reveals these. They tell you it is clean. A program that passes all 4 is production ready. Before we write tests, let's define what a test case actually is. It is a specific input paired with its expected output, used to verify correct behavior. It has 3 parts: the input, the arguments and files; the expected output, the standard out, the standard error, and the exit code; and a description of what it tests. All 3 parts matter. Without an expected output, you cannot tell pass from fail. Without a description, you cannot tell what broke when it fails. And before you can run any tests, you need test input files, each targeting a specific scenario. Keep them in a test subdirectory. Let's create the test input files, 1 per scenario. First, the normal case. Use cat with a here document to write 2 lines with mixed case and punctuation into test/normal.txt. Then the edge cases. Touch creates an empty file of 0 bytes. Printf hello with no new line makes a single word file. Echo 5 copies of same makes an all identical file. Printf with only punctuation makes a punctuation only file. And a tiny Python one-liner prints the letter 100 times to make a word far longer than the 63-character limit. This is what each file tests, and what the program should do. Empty.txt is an empty file of 0 bytes. It should print nothing and exit 0. Singleword.txt has 1 word with no new line. It should print 1, then hello and exit 0. All same.txt has 5 identical words. It should print 5, then same on one line. Only punctuation.txt has no letters at all. It should print nothing and exit 0. And longword.txt has a 100-character word, which should be truncated to 63 characters. These files take minutes to make, and the bugs they catch would take hours to find. Running each test by hand is tedious and error-prone. You will skip tests, misread output, or forget to check the exit code. A script automates the whole thing. This is the core helper run test. It takes a description, the expected output, then the command to run. It runs the command, capturing standard out, and redirects standard error to dev null so error messages do not contaminate the comparison. Then it compares actual to expected. If they match, it prints pass and increments the pass counter. If they differ, it prints fail, shows expected and actual side by side, and increments the fail counter. That side-by-side output makes diagnosis instant. Now the test cases themselves, grouped by category. Under normal tests, we check the default top 10 output and the top 3 output, both against the normal file. Under edge tests, we check that the empty file prints nothing, the single word file prints one hello, and the punctuation-only file prints nothing. Under error tests, we use a second helper run test exit which checks only the exit code. We verify that no arguments exits 1, a non-existent file exits 1, and an invalid dash and value like a BC exits 1. For output tests, we compare the text. For error tests, we check the exit code because the exact message is an implementation detail. Make the script executable, then run it. This is the output. Under normal tests, both cases pass. Under edge tests, the empty file, the single word, and the punctuation-only file all pass. Under error tests, no arguments, non-existent file, and invalid dash and all pass, each exiting with code 1. At the bottom, the results: 8 passed, 0 failed. This whole run takes a fraction of a second, and every time you change the code, you run this again and instantly know whether anything broke. Now an important testing principle. The no arguments test checks only the exit code, not the exact printed text. Why? Because the spec says to print a usage message to standard error, but the exact wording is an implementation detail, not a requirement. If you hardcode the message text, a minor wording change breaks the test, even though the program is still correct. That is a fragile test. Testing the exit code verifies the real requirement without being brittle. Passing all the output tests means the program produces correct output and handles errors gracefully, but it does not mean it is free of memory bugs. A leak, memory allocated but never freed, does not change the output at all. These bugs are invisible to output tests. Valgrind catches them. Here we run it on the normal test, with leak check full and error exit code 1. It reports all heap blocks were freed, no leaks are possible, and 0 errors. But here is the key discipline. Run Valgrind on every input, normal, edge, and error, not just the happy path. A leak may hide on a path your normal test never touches. This is the critical one. Error paths are exactly where leaks like to hide. Think about what happens when fopen fails. The program prints an error and exits 1, but does it free the word list before it returns? Here we run Valgrind on a non-existent file. It prints the no such file or directory message, and then all heap blocks were freed, 0 errors. This confirms the error path calls word list free before returning. And here is the subtle point. The visible output, the error message and the exit code would have been correct whether or not we freed the list. Only Valgrind can tell you the error path also cleaned up. There is a subtler kind of testing called integration testing. It verifies that the modules work correctly together, not just individually. Integration tests exercise the interfaces between modules, data flowing from file I/O through word count to output via main. Each module might be correct on its own, yet they can still disagree at their boundaries about data formats or who owns allocated memory. This is a focused integration test. We make a file with words separated by commas. Running WordFreak on it gives a 3, B2, C1. This proves file I/O treats commas as separators, not just spaces, and the counts flow correctly through word count to the sorted output. If word extraction only split on whitespace, this test would fail. Let's deliberately introduce a leak and find it. Comment out the word list free call on the error path, rebuild, and run Valgrind on a non-existent file. Now it reports a leak in 2 blocks, 16 bytes definitely lost, and 1088 bytes indirectly lost. Why 2 blocks? Look at the figure. Word list create allocates twice, once for the small word list struct and once for the larger entries array it points to. When you skip word list free, the struct is definitely lost because nothing points to it anymore. And the entries array is indirectly lost because it was only reachable through that now lost struct. Both need freeing and word list free handles both. Uncomment it, rebuild, and Valgrind reports 0 leaks again. This is the whole test suite as a matrix, every category and its result. Normal tests, the default top 10 and the top 3 pass. Edge test, empty single word, all same and punctuation pass. Error tests, no arguments, bad file and bad -n pass. Memory tests, Valgrind on all inputs including the error paths pass. An integration, the comma-separated words test, passes. Every row is green, and every requirement from the spec now maps to a passing test. That is what done means. One more idea, and it is a powerful one, regression testing. Suppose you improve the word extraction loop to make it faster. After the change, the normal output still looks right, but did you break the comma test, the long word test? You cannot tell by checking one case, so you rerun the whole script. If all tests pass, the change is safe. If even one fails, you introduced a regression, a bug in something that used to work. This is the real value of automated testing. A test suite is a safety net. It catches regressions the moment they happen, in seconds, not in production. Let's finish with 2 common mistakes. The first is testing only the happy path. What you do is run WordFreak on the normal file, see correct output, and declare testing complete. What happens is you miss the empty file that segfaults, the file not found path that leaks, and the single word input with an offby one. These only appear with inputs your normal file never exercises. The fix: test all 4 categories, normal, edge, error, and memory. Use the edge case table as a checklist and write a test for every row. The second mistake is running Valgrind on only one input. What you do is run Valgrind on the normal file, see 0 errors, and declare the program memory correct. What happens is that leaks often occur on specific paths. The normal path frees everything. The error path might skip word list free. The empty file path might return before freeing a loop buffer. Each path needs its own check. The fix: run val grind on every input, normal, edge, and error. A leak that occurs only on the error path is still a leak. Let's recap and close out the course. Testing is what turns a program that works on your file into a program that is correct. Cover 4 categories. Normal inputs verify basic functionality. Edge cases probe boundaries. Error tests verify graceful failure. And memory tests catch invisible bugs. An automated script reruns every test in seconds. You run val grind on every path because leaks hide on error paths. Integration tests verify your modules agree at their boundaries. And a test suite is a regression safety net you run after every change. And with that, you have finished the journey. Over 12 chapters, you went from printf hello world to a multi-module, specification-driven, systematically tested utility. You can write C, you can build real software in C, congratulations, and keep building.